next we're going to cover part 1 of L'Hopital's rule. I should write part 1. In homework and quizzes, for many limits, it says in the directions you may not use L'Hopital's rule, whatever that is. So for those of you who have not seen calculus, you would have no idea what that is until now. And you'll see why people who have seen calculus would want to use it, or could want to use it. But our discussion of L'Hopital's rule, we will break into 2 parts. The second part we'll cover next week is lecture, 8.1. But here, well, let's state the result and then do a couple examples. The result, if direct substitution for limit as x goes to a of a quotient gives 0 over 0, or n infinity over n infinity, then the limit of that quotient is given by the limit of the derivative of the top divided by the derivative of the bottom. So earlier in the semester when we were doing limits, we didn't have derivatives, and we didn't have this rule. So we couldn't use this rule. But now we have derivatives, so we can use this rule to take some limits. And notice it works only if the direct substitution gives a 0 over 0 or an infinity over an infinity. We can use it to compute limits. It also works for limits as x goes to infinity or negative infinity. So let's look at a couple examples. Let's look at, 4 or 5 examples. Example. Compute this limit. Limit as x approaches 4 of x squared minus 3x minus 4 over x squared minus 2x minus 8. And I'll also show how I would like you to notate that you're using L'Hopital's rule. So here a direct substitution gives a 0 over 0, 16 minus 12 minus 4 over 16 minus 8 minus 8, 0 over 0. So we can use L'Hopital's rule. By L'Hopital's rule, and I'll just make a note, but that's because of the 0 over 0. By L'Hopital's rule, maybe I'll put the 0 over 0 up here somewhere. You can put it wherever you want, as long as you note that it is a form on which you can apply L'Hopital's rule. But by L'Hopital's rule, we can compute that limit by computing this limit. It's still as x approaches 4. Just looking at a couple other examples. But the rule says the limit of the quotient is given by the limit of the quotient of the derivatives. So the derivative of the top is 2x minus 3. Derivative of the top. Derivative of the bottom is 2x minus 2. Well, now, what happens if we try to take the limit? Well, we get 8 minus 3 over 8 minus 2, which is 5 over 6. So here, we use L'Hopital's rule, and then we were able to take the limit. Notice in using L'Hopital's rule, we're not using a quotient rule. This doesn't say to take the derivative of the quotient. This says to take the derivative of the top and the derivative of the bottom, the quotient of the derivatives. So L'Hopital's rule does not use a quotient rule. Let's look at this result. So when we were discussing squeeze theorem, we showed that this limit was 1 using a lengthy argument with a large unit circle diagram. But here with L'Hopital's rule, notice L'Hopital's rule does apply because sine of 0 is 0. The bottom, as x goes to 0, goes to 0. So L'Hopital's rule does apply. It's a 0 over 0. So the limit is now this limit. Derivative on the top, derivative of sine x is cosine x. Derivative on the bottom is derivative of x, which is 1. And cosine of 0, we can now take the limit. Cosine of 0 is 1. The bottom is 1. So we have a second proof for this limit being 1. let's look at a couple more examples. Maybe 4 more examples. Yeah, I think 4 more examples. Compute this limit. Limit as x approaches 0. E to the x minus 1 all over x squared. Well, again, you try a substitution, you get 0 over 0, because e to the 0 is 1, so you get 1 minus 0 minus 1, which is a 0. You get 0 squared, which is a 0. So you can apply L'Hopital's rule. That limit now equals this limit. Derivative of the bottom is 2x. What's the derivative of the top? E to the x minus 1. Derivative of the top, derivative e to the x is itself. Derivative of negative x, negative 1. Derivative of negative 1 is 0. And what happens if you try to take this limit? Well, you get e to the 0 minus 1, which is a 0, over 2 times 0. So again, we get a 0 over 0. We can apply L'Hopital's rule a second time. That's fine. We can apply L'Hopital's rule to this limit now. And we get that it equals this limit. Derivative on the bottom is 2. Derivative on the top is e to the x. And as x approaches 0, e to the x approaches 1. 2 approaches 2. So that limit is 1/2. So L'Hopital's rule does also apply to limits as x goes to infinity, provided that it still takes one of those forms. So there's no direct substitution with infinity, but take one of the forms means, let the limit on top go to infinity, let the limit on the bottom go to infinity. And if it's a 0 over 0 or an infinity over infinity, you can apply L'Hopital's rule. Here, we have the limit as x goes to infinity, e to the 5x over x squared. Well, e to the x, remember, goes off to infinity as x goes to infinity. So raising that to the 5th power is still going to cause that to blow off to infinity. So you get an infinity on top. As x goes to infinity, x squared goes to infinity. We have an infinity over infinity, so we can apply L'Hopital's rule. So that limit now equals this limit. Derivative on the top is 5e to the 5x. Derivative on the bottom is 2x. What does this limit equal? Well, let the top and bottom go to infinity, and again, you get an infinity over an infinity. So again, we can apply L'Hopital's rule. Sometimes you can get trapped in a L'Hopital's rule cycle where things never simplify, or things upon applying the rule, things get more complicated. That is possible. But what happens here? We get limit as x goes to infinity, 25 e to the 5x over 2. 25 because of a second 5 from the chain rule. And what does this limit equal? Well, we can pull out the 25 halves if we want. You don't have to. But as x goes to infinity, e to the 5x goes to infinity. Multiplying that by a 25 halves will not change the fact that it is infinite. So in that one, in both of those, we had L'Hopital's rule being applied twice. Let's do one more application of L'Hopital's rule. So that also works for limits as x goes to negative infinity, provided it takes the form. Example. Find the horizontal... Oh, I should have mentioned, the very first example we did, some of you may have noticed this, the very first example we did where we got 5/6, you could have done that with factoring. find the horizontal asymptotes. Why not? Let's also find the vertical asymptotes. That's easy enough. Find the horizontal and vertical asymptotes of this function. Find the horizontal and vertical asymptotes. Well, remember, for a horizontal asymptote, a horizontal asymptote could be described by the behavior as the function goes to positive infinity, or by the behavior of the function as x goes to negative infinity. So let's find the horizontal asymptotes first. We need the limit as x goes to infinity of our function. As x goes to infinity, a polynomial, I guess we didn't really discuss this in detail. We did kind of mention it a little. A polynomial is dominated by its largest term as x gets larger. So here, the top will go to a positive infinity because that 2x squared is going to take over the 3x. So the top, as x goes to infinity, goes to an infinity. The bottom is going to go to negative infinity because there's a negative coefficient on the x squared. Infinity over negative infinity is a form on which L'Hopital's rule applies. So that limit is now equal to this limit. Derivative on top, 4x plus 3, derivative on the bottom, negative 10x. As x goes to infinity, again, we have an infinity on top, and we have a negative infinity on the bottom. A form on which L'Hopital's rule applies. Derivative on top is 4, derivative on the bottom is negative 10. So this limit is negative 2/5. Negative 2/5 does not change as x goes to infinity. But we also need the limit as x goes to negative infinity. And here you could do the translation into a limit as x goes to positive infinity if you want, or you could do it directly. I'm going to do it directly because it illustrates L'Hopital's rule with x going to negative infinity. But you could turn into a limit as x goes to positive infinity, and the only difference will be that sign on the 3, and you'll see that you get negative 2/5. But what happens here as x goes to negative infinity? Well, here we have still an infinity on top because we're squaring the largest exponent term. So that makes this a positive. So we get an infinity. On the bottom we have negative 5 times an infinity. So that's a negative infinity. Apply L'Hopital's rule. Limit as x goes to negative infinity of 4x plus 3 over negative 10x. And here we're going to apply L'Hopital's rule again when we can, because what form does this take? Well, the top goes to negative infinity as x goes to negative infinity. The bottom goes to positive infinity as x goes to negative infinity, because the negative 10 will cause that to flip over to the positive side. We can apply L'Hopital's rule. So it's a limit as x goes to negative infinity of 4 over negative 10, which again equals negative 2/5. Negative 2/5 does not change as x goes to negative infinity. So f of x, we have to remember what we're being asked. We're not asked to just find those limits. Has horizontal asymptote. There's only one of them. Y equals negative 2/5. So there's an illustration, another illustration of L'Hopital's rule. But this also asks for vertical asymptotes, so we might as well find them. Well, we have to find them since it asks. Vertical asymptotes, remember, set the bottom equal to 0. Add 5x squared. Divide by 5. So x equals the positive or the negative root 2/5. So f of x has vertical asymptotes. root negative 2/5, and horizontal asymptotes negative 2/5, positive negative root 2/5, horizontal asymptote negative 2/5, and in my notes, I did not have that vertical asymptote computation, so I didn't know these were both going to have 2/5 being thrown out. That was a nice coincidence. So right here we discussed one form L'Hopital's rule could take. Well, we described the form that L'Hopital's rule applies to. We'll see next week there are some other forms we could play around with and make them take one of these fractional 0 over 0 or infinity over infinity forms. But for now, let's just practice these types of examples.